Hi everyone. So welcome back for section. So this week we're going over the correlation analysis lecture. Does anyone have any questions first before we get started? Okay, so Michael has a question. He asked, correlation between IQ and Obama vote is 0.45. What is the correlation after changing IQ into a z-score and keeping Obama vote the same? So let's take a look here first. Okay. So just to address your question, Michael, let's talk about first. Let's talk about correlation, and then let's talk about z-scores and how z-scores affect things. Right. So, what does correlation tell us? What is a correlation of 0.45 tell us about our data? So this is what correlation of 0.45, a moderately strong positive relationship. Yeah, that's great. So that's what we would say about correlation of 0.45. There's a moderately strong positive linear relationship between these two variables. And then your question is, after changing IQ into a z-score and keeping Obama votes the same, how would correlation change, right? So let's talk about z-scores. So what is a z-score and why do we use them? Okay, so let's talk about z-scores, right? So this is a z-score. when we talk about z-scores, it's a linear transformation of data. And the whole idea of the z-score is it's used to standardize our data, right? So the whole idea is this is the calculation for a z-score. We take each value of x and we subtract out the mean of x and we divide by the standard deviation. And by doing that, we create a new data set, a new sample where the mean of that sample is now 0 and the variance is now 1. So this will standardize our data so that we know that the mean will be 0 and the variance will be 1, right? So we use an example here, and we talk about taking a look at admissions exams from high school, right? And we're looking at two students. One took the ACT, the other one took the SAT, and we want to compare the two. So how can we do that? Well, this is a good example of using z-scores, and we could calculate each of the two students' z-score on their respective exam. So if we calculate so if we calculate each of the two students' respective z-scores, we can then compare the two, right? So we have the ACT. Megan scored a 26 on the ACT, and Jasmine scored a 900 on the SAT. So if we just look at those two, they're in different scales, right? They're not on the same scoring scale at all. And if we just wanted to compare them and we didn't know anything about the SAT and the ACT and how it's scored and what it's out of, we wouldn't be able to compare those two students on their own. So that's why we use a z-score. We use a z-score transformation in order to get the two students looking in the same scale and looking at how they scored compared to their peers. So in other words, we could actually calculate a z-score here. And why don't we do this as a good example? Why don't we go through this example together and calculate what each of their z-scores are. So let's calculate what Megan's z-score is and what Jasmine's z-score is. You have all the information here in order to do that calculation. So we said earlier that the way we calculate a z-score is we take their data point, we subtract out the mean of the greater population, and then we can divide it by the standard deviation. So we can do that here to calculate what the z-score is for each of them. Right, so Megan has a z-score of 2, exactly right. And we calculate that because she scored 26. The mean was 22, so if we subtract 26 by 22, we get 4, and then we divide the standard deviation 2. And we come up with an answer of 2, because 4 divided by 2 is equal to 2. So that means that Megan scored 2 standard deviations higher than the mean on the ACT. And let's calculate what Jasmine's score was, her z-score on the SAT, and see if we can compare the two to see who scored better. So Jasmine had a -1 z-score because she had an SAT of 900 and the average was 1,000. If we subtract 900, if we subtract 1,000 by 900, we're getting -100, and then we're going to divide by the standard deviation of 100. So -100 divided by 100 is equal to -1. So that's absolutely right. So that means that Jasmine scored 1 standard deviation below the mean on the SAT, while Megan scored 2 standard deviations higher on the ACT than her peers. So if you're a college admissions officer, who would you say scored better on their test relative to their peers here? Megan. Yeah, exactly right. So she scored 2 standard deviations higher than the mean on the ACT, while Jasmine actually scored 1 standard deviation lower than the mean here. So what can we conclude about z-scores? What do they do about our data? It's a linear transformation, right? But if you look at the data, if you look at everyone in the data, no matter what the numbers are, right? So say you're looking at Megan, right? And her score was 26. If you compare 26 and 22, it's still going to be higher, right? And 2 is higher than 0, right? So the whole point of a z-score is instead of saying the mean ACT score is 22, we could say that a z-score of 0 is representative of 22 on the ACT. And here we're saying that a z-score of 2 is representative of a score of 26 on the ACT, right? So really what it's doing is it's standardizing our data here, but it's also maintaining that relationship between the data. It's a linear transformation, so that means that the order is preserved and the distribution of that data set is still preserved. Does that make sense? Great. So since that relationship is it's not being altered, since the relationship, the spread of the data is going to be the same, because it's a linear transformation, what would happen to the correlation in that case between these two variables? Yeah, it would stay the same, exactly right. Because, so whether we're dealing with the actual IQ values or whether we're dealing with the z-scores of the IQ values, that relationship between that and another variable is going to be the same, right? Because it won't affect the correlation. Because if we plot those values, if we plot each of these values, the relationship between the two is still going to be the same. It's just in a different scale, right? But as far as whether we're dealing with 26 or 2, it's going to be the same trend, right? The numbers might change of the variables, of the variable itself, but as far as the relationship goes between IQ and the z-score for IQ, it should stay the same. Does that make sense, Michael? So just to give another example about z-scores, which you might be familiar with. So if you have children, or if you remember back to when you were a child yourself and you go to the pediatrician, what they do is they track your height and your weight relative to everyone else in your age group. So they'll say that you might be the 75th percentile for height or the 25th percentile for height. So what we're doing there is that's basically looking at a z-score, right? Is we're saying your height of, let's say you're 5 foot, your height of 5 foot compared to the average for your age group, which might be, let's say it's 4'8" or something. That would mean that you're higher than the mean, and it gives you a indication of where you fit in relative to all your peers. So that's an example of a z-score, right? But whether we're dealing with the absolute numbers of 5 foot or we're dealing with the z-score, let's say your z-score in that case would be 0.5, okay? It doesn't, the relationship is still going to remain the same because the numbers are going to be relative to one another, right? So your z-score of 0.5 is still going to be higher than 0, and your height of 5 foot is still going to be higher than 4'8". So what's an example? What kind of an example can we think of that would actually change the correlation? How could we change what kind of transformation can we do to change the correlation of two variables? Yeah, so that's a good example. Squaring all the events of one variable. So that's not a linear transformation. That's what's called an exponential transformation by squaring all the events in a certain variable. So we can imagine that that would change the correlation because the correlation would then change from your original data to the squares of all your data. That can have a great effect on the correlation. In some cases, it's actually necessary. We actually look at exponential transformations, and that actually gives us more information than looking at the original information, but that's definitely a transformation that would affect the correlation between those two variables. Does that make sense? But as far as the z-score is concerned, it's not going to affect it because the z-score is just a standardization. It's a linear transformation. So everything that you're doing to the variable is being done to every single observation in that variable, and it's preserving the relationship between the data. If you're going to square all the events, that's going to alter the relationship because you might have had linear data, but now you're dealing with exponential data, and the correlation can vary from that transformation. That's a great example. And does that make sense? Is that a little bit more clear? I can give you another example. Let's say if I'm dealing with length, if one of my variables is in feet, right, and I want to convert it to inches, that variable I'm going to convert feet to inches, and say I'm looking at height and weight, right? So in one example, I have everyone's height in feet, and I want to change that to height in inches, and I'm still comparing it versus weight in both examples. Will the correlation change by applying that transformation? No, it won't. Right. Exactly. So the units don't matter. It's more so the relationship between those two variables. So that's a way of looking at it is if I apply this transformation, will the relationship between these two variables, will that change? If it's not going to change, then your correlation won't change, right? And you can think of it, right? It doesn't matter if I say that you're 6 foot or the equivalent in inches, right? Which is 6 times 12, 72, right? So whether I say you're 6 foot or if I say you're 72 inches, they're equivalent. So as far as your height in inches compared to your weight versus everyone else and your peers, it's going to have the same trend. So it's going to remain this. It's going to have the same correlation. Hope that answers that question. Do we have any other questions that we want to take a look at? Is everyone okay? Let's look at this rule. Yeah, so we can talk about that. So let's talk about the empirical rule, right? So what the empirical rule tells us and how we can use it to better understand the idea of z-scores and the idea of how data is distributive. So the whole idea behind the empirical rule, first of all, is there's going to be something called the law. Hold on, let me see. I just want to see if we covered it yet. Okay. So first of all, there's something called the law of large numbers, which is to say that as we take larger and larger samplings of things, you're going to see a trend, and you're going to see a symmetry if you plot that, and it's going to appear to be a mound-shaped data set. And the reason why that is because you're going to see the majority of instances are going to fall into the mean, and then the extremes are going to be at the tail regions, which are less likely to occur. Okay, so let's just take a simple example, and let's think about this, right? So when you flip a coin, right, back to the probability lecture, there's a 50% chance that you're going to get heads, or a 50% chance that you're going to get tails, right? So if we were to flip a coin 10 times, we would expect that you would get 5 heads and 5 tails, right? But that would be mathematically the case, right? But it doesn't always work out that way. So you could flip a coin 10 times. Sometimes you might get 6 heads. Sometimes you might get 7 heads, right? Sometimes you might get all heads. It's very possible for you to flip a coin 10 times to get 10 heads. It's not likely to happen, but it's possible, right? So if you were just to keep flipping that coin 10 times and then writing down what your distribution is and then flipping it again and again and again, and if you plot that, the more times you flip the coin, the more data you're going to have, and it's going to appear, you're going to see this mound shape appear, right? And it's also the case, so that's just simply, so if we were to look at that distribution, we would find that the mean would be 5 times head and 5 times tails. And then at the two extremes, we would see there would be, it's very, very unlikely to get 10 heads, but it's possible, and that would appear at that bottom. So that's just the idea of why data appears in a mound shape and why it's symmetrical. if we have a large enough sample size. That's kind of the idea of it. And secondly, then we can then use z-scores, the idea of z-scores, right? The idea of z-scores are that we can standardize any data set and apply it to a distribution where the mean is 0 and the standard deviation will be 1. Okay? So let me see if we have a figure here. Okay. Let me pull up a figure for us. So if we look here, this is the Gaussian distribution, that mound-shaped distribution. And with the z-score, the mean, the center here, this is the most likely occurrence, right? This is, we learned about the mode, so we can say that this will be the mode of the distribution. It's also the mean, right? So the mean in a z-score distribution will be equal to 0. And then if we look +1 and minus 1, this is going to be +1 standard deviation. So this will be a z-score of 1. And this will be -1 standard deviation. This will be a z-score of -1. And we know with the empirical rule that we can actually estimate, we can guesstimate that the data that falls in between +1 and -1 standard deviation from the mean will represent about 68% of your data. And then within 2, we'll have 95% that will fall within 2 standard deviations. And finally, if we look + and -3 standard deviations, that will encompass 99.7% of our data. So practically all of it, right? And let's go back to the lecture. And so the caveat here is it's only going to apply to data which is symmetrical. So we have to make sure that the data is what's called normal. It's normally distributed, or it's symmetrical. And that happens with large numbers because of that law that we spoke about earlier. But if you have a small sample size, you have to make sure that you have to see that the data set is normal first before you can apply the empirical rule. So here we're giving an example here with Facebook friends, and we're looking at this data set. So we could say it's roughly mound-shaped. It has roughly that same shape that we just looked at, the symmetrical result. And here, this is using R. We found the mean and the standard deviation. And using the empirical rule, we can prove that 68% falls between ±1 standard deviation. And also for 2, you have 95%. So if we have non-symmetric data, so the empirical rule is used when we have symmetric data, or a sample size that's large enough that we can assume normality. If we can't assume that we have a normal distribution or that the distribution is symmetrical, we can use this rule, Chebyshev's rule, in order to estimate the amount of the percentage of data so basically the empirical rule, but applied for non-symmetrical data. And this is how Chebyshev's rule is calculated here, that we can say for any set of data where for any number k where k is greater than 1, the proportion of the data that lies within k standard deviations of the mean is at least 1 minus k squared. 1 minus 1 over k squared. So if we look here, if we look at the proportion of the data that lies within k standard deviations of the mean, if k is equal to 2, we can solve that and find that 75%, at least 75% of the data falls within 2 standard deviations of the mean. So the whole idea here is because the data is not normal, it's giving a little bit more error. So it's saying that at least 75% of the data falls within 2 standard deviations of the mean, while if it was normal, we would say there's 95% of the data. So this gives you a little bit more, it's a little bit more error prone to account for that non-normality. And it can be used for distributions that are not symmetric, right? So the reason why these rules work is what I was saying before, is that there's a law of large numbers, and let me show you an example of that.
This is Jim.
So we can
How does an insurance company decide how much to charge for car insurance? How do casinos set up payout structures to make sure that they make a profit? How does a poker player decide whether or not to fold? How do we efficiently measure the appeal of a political candidate? The answers to these questions are informed by the law of large numbers. The law of large numbers states that as the number of trials or observations increases, the actual or observed probability approaches the theoretical or expected probability. This is important to understand because it allows us to predict and have confidence in how events will play out in the long run. Let's take a common example, flipping a coin. Assuming the coin is fair, we know that the theoretical probability of flipping heads is 0.5 or 50%. However, that doesn't guarantee that if we flip a coin 10 times, we'll get 5 heads. But we can be confident that as we continue flipping a coin indefinitely, the cumulative proportion of heads flipped should get closer and closer to 50%. Looking at this graphically helps to illustrate the concept. I just flipped a coin 20 times and these are the results. After each flip, we'll calculate the cumulative proportion of heads so far. So the first flip is tails. So our current proportion is 0 heads out of 1 flip, 0%. The second flip is also tails. So now it's 0 heads out of 2 flips, still 0% heads. Next flip is tails again, 0%. Then heads. Now we have 1 heads out of 4 flips, 25% heads. Flip again and it's heads, 40%. Heads again, and we finally hit our theoretical probability of 50% for the first time. Let's keep going. This graph shows the observed probability approaching the theoretical probability. One common misconception, referred to as the gambler's fallacy, is that if the first 4 flips were tails, you're more likely to get heads on the next flip because the proportion is supposed to even out to 50% heads. This is not the case because each flip of a coin is an independent event. Its outcome is unaffected by all previous events. So if you start out with 4 tails in a row, it's not that you're more likely to get heads. It's just that in the grand scheme of things, 4 tails flips will get averaged with a huge number of flips that are expected to yield an even number of heads and tails, causing the proportion to approach 50% as the number of trials increases. Another version of the law of large numbers explains that the more people from a population that you sample, so the larger your sample size, assuming your sample is free from bias, the closer your sample average will be to the population average. Let's say you have a group of 100 people. Each has some number of dollars in their wallet. If we ask one person how much money she has in her wallet, we'll get our first observation, $49, which might be pretty far from the average of the group. After asking the second person, $29, and averaging that value with the first, we are likely to have a better estimate of the group average. As we continue this process of adding observations and thereby increasing our sample size, we'll generally get better and better estimates of the group's average. So the law of large numbers gives us a compass with which to navigate the randomness around us. Even though we can never predict the outcome of a single coin flip, we can know that over time about half of the flips will be heads. And in general, the principle supports the idea that a well-founded strategy that is followed consistently should win out over time, even though it might result in a few negative events along the way. Thanks for watching. See you next time.
So that was kind of a cute basic video on the law of large numbers. Also, the central limit theorem is also talking about the same concept. And the idea is if you sample a large amount of people, you're going to find the symmetrical result that occurs if we graph that. And from there, we can apply the empirical rule, which is a mathematical way of estimating what proportion of the people will fall within these different standard deviations. And because of the law of large numbers, it then follows that we can estimate that plus minus 1 standard deviation, we have about 68% that falls within 1 standard deviation, within 2, 95%, and within 3, 99.7%. So this topic, it builds off of the previous one of probability, as we see with the the idea of probable events and improbable events. And now we're taking it one step further. We're teaching about z-scores and how we can standardize our data. And then from there, we can talk about the empirical rule and how the data will fall within this trend, okay? So if we talk about z-scores, right, and we plot our data with its representative z-scores, remember, this mean will be a z-score of 0, this will be a z-score of 1, this will be a z-score of 2, and this will be a z-score of 3 here, right? So as we spoke about earlier, right, we calculated Meg's z-score, right, and she was the girl who scored a 26 on the ACT, right, and the mean was 22, right, and we said the standard deviation was 2. So we said her z-score was +2, right? So because her z-score was +2, we can then use the empirical rule to calculate what her percentage on the SAT was. So just like we were talking before about going to the pediatrician's office and finding what percentage you are in your weight or your height, we could do the same thing here with the SAT scores, right? And we see here that +1 standard deviation will be 34, right? So first of all, let's add all this up, right? So there's 50% to the left and 50% to the right, right? So if you scored the average, 20, what would you say, it was 22, that would mean you were at the 50 percentile, right? If you scored 1 standard deviation above the mean, right, so it was 22 plus 2, which is 24, you would then be 50 plus 34%. So you'd be in the 84th percentile on the ACT. Now, if you scored 2 standard deviations above the mean, so if you scored actually what Megan got, which was a 26, right, that would be 84 plus 13.5, which is the 97.5th percentile. So we could say that Megan scored 97.5% higher than her peers. She's in the 97.5 percentile on the ACT. And we know that here from the empirical rule. So we're also going to teach you in further lectures, we're also going to teach you how to calculate the exact percentages. We can calculate that using R and using z-scores. And we'll have more material that builds upon this material, but the idea of why the empirical rule works and how these work, these rules came up by mathematicians, by statisticians who came up with these rules, but the whole concept of it is built upon the concept of the law of large numbers and the central limit theorem, which would say that as your sampling increases, your data is going to get more and more normal, and it's going to fit this distribution more and more. So that's an important concept to know, that in sampling, we need to have a large number in order to assume normality. Otherwise, we actually have to look at how the data looks to see if it fits this normal distribution, this mound-shaped data. So practically speaking, the empirical rule or statistical tools will be based on the normal distribution. If it's not normal, if you're not dealing with symmetric or normal data, we would then have to use some other rules, some other methods in order to deal with that data. But typically, we're most often dealing with normal data or data that we can assume normality with. And in the case of Chebyshev's rule, that's used for data where it's non-symmetrical. So it's an example of how to use the empirical rule when you don't have symmetrical data, and that's why it's a little bit more loose in regards to its answers. So we saw here that with the normal distribution within ±2 standard deviations, you're encompassing 95% of the data. With Chebyshev's rule, you're only encompassing 75% of the data because it's allowing for more of that error because you're not dealing with symmetrical data. Does that make sense a little bit more and help answer your question? The whole idea is we're trying to look at the variation within the data and account for that. Okay, great. Did you have some other questions, Michael? Or for that matter, does anyone else have any other questions? So here's just an example of the central limit theorem. So it shows that as we increase our sample size, 1, 2, 3, 4, and 5, it becomes more and more normal. So the greater our sample size, the more we're going to get to that true mean, and the less deviation we'll have. And the empirical rule will be that much more accurate. And feel free to ask any other questions, but this might be another good video in case it's still kind of confusing. We can listen to this video about the central limit theorem.
In this video, I want to talk about what is easily one of the most fundamental and profound concepts in statistics, and maybe in all of mathematics, and that's the central limit theorem. Central limit theorem. And what it tells us is we can start off with any distribution that has a well-defined mean and variance, and if it has a well-defined variance, it has a well-defined standard deviation. And it could be a continuous distribution or a discrete one. I'll draw a discrete one just because it's easier to imagine, at least for the purposes of this video. So let's say I have a discrete probability distribution function, and I want to be very careful not to make it look anything close to a normal distribution because I want to show you the power of the central limit theorem. So let's say I have a distribution. Let's say it could take on values 1 through 6. 1, 2, 3, 4, 5, 6. It's some kind of crazy dice that's very likely to get a 1. Let's say it's impossible. Let me make that a straight line. You're very high likelihood of getting a 1. Let's say it's impossible to get a 2. Let's say it's an okay likelihood of getting a 3 or a 4. Let's say it's impossible to get a 5. And let's say it's very likely to get a 6 like that. So that's my probability distribution function. If I were to draw a mean, this is symmetric, so maybe the mean would be something like that. The mean would be halfway, so that would be my mean right there. The standard deviation, maybe it'd be that far and that far above and below the mean. But that's my discrete probability distribution function. Now what I'm going to do here, instead of just taking samples of this random variable that's described by this probability distribution function, I'm going to take samples of it, but I'm going to average the samples and then look at those samples and see the frequency of the averages that I get. And when I say average, I mean the mean. So let's say, let me define something. Let's say my sample size, and I could put any number here, but let's say first off we try a sample size of n is equal to 4. And what that means is I'm going to take 4 samples from this. So let's say the first time I take 4 samples, so my sample size is 4. Let's say I get a 1, let's say I get another 1, and let's say I get a 3, and I get a 6. So that right there is my first sample of sample size 4. And I know the terminology can get confusing because this is a sample that's made up of 4 samples. But when we talk about the sample mean and the sampling distribution of the sample mean, which we're going to talk more and more about over the next few videos, normally the sample refers to the set of samples from your distribution, and the sample size tells you how many you actually took from your distribution. But the terminology can be very confusing because you could easily view one of these as a sample. But we're taking 4 samples from here. We have a sample size of 4. And what I'm going to do is I'm going to average them. So let's say the mean, I want to be very careful when I say average, the mean of this first sample of size 4 is what? 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 6 is 11, 11 divided by 4 is what? 2.75. 2.75. That is my first sample mean for my first sample of size 4. Let me do another one. My second sample of size 4, let's say that I get a 3, 4, let's say I get another 3, and let's say I get a 1. I just didn't happen to get a 6 that time. And notice, I can't get a 2 or a 5. It's impossible for this distribution. The chance of getting a 2 or 5 is more, because I really want to make it clear what we're doing here. So I do one more. Actually, we're going to do a gazillion more, but let me just do one more in detail. So let's say my third sample.
His idea here,
size,
as you see, is he's taking more and more samples from this data, and he's coming up with the same mean. This is kind of where he's getting at. But if you plot it, and if you keep taking more and more samples from that,
sample mean. So
you're going to see that you have a true mean emerging. And this is where the majority of the cases will be.
Starting to approximate a normal distribution. And that is the neat thing about the central limit theorem. So the central limit, and this was the case for, so in orange, that's the case for n is equal to 4. This was for sample size of 4. Now, if I did the same thing with a sample size of maybe 20. So in this case, instead of just taking 4 samples from my original crazy distribution, every sample, I take 20 instances of my, that if I were to plot the sample, 10,000, well, let me, the same mean, bottom theorem, getting very close to a normal distribution, in fact, 100. And we were to take a...
That's kind of the example. That might have been not the best video to show, but Khan Academy usually has great videos. But the idea is, as we're increasing the sample size, we're going to have more, the data is going to take on more and more of a normal distribution, and the empirical rule is going to be that much more accurate when we have a larger sample size. So that's the whole idea behind why the empirical rule works. It works because of these other theorems, because of the central limit theorem, and because of the law of large numbers, which says that as we take more and more samples, this probability, you're more likely to see this true probability emerge as the center and the mean, and then on those tails, you're going to have the less probable events. So you're going to see this mound shape occur, with the center being the most probable occurrence, and then on those 2 tails, you're going to have the least likely occurrences. So those are less likely to occur. So, if you use the coin flip example, you're going to see, if you flip a coin 10 times, you're going to see in the center, there'll be 5 heads, 5 tails. On those 2 tails, you're going to see 10 heads and 0 tails. So it's not to say that it's impossible, it's just very, very unlikely to occur. And that's the math and the understanding behind these theorems that we have. And in further lectures, we're also going to build upon this concept some more. So I'm glad we were able to answer a few of those questions. Do you have any other quick questions that I can quickly help out with? We're going to cover this a lot more in the sampling in the second half of the class, but it's good for us to even just start these discussions now, so that we can get familiar with z-scores and sampling. We're going to cover this in much more detail in upcoming lectures, but specifically the z-scores and sampling and the empirical rule. But certain topics do build upon the previous ones. So it's good to be aware of all of this. And so for this week, the main takeaways are we're looking at correlation analysis. So we went over scatter plots, we went over covariance and correlation and what each of these mean. And we had an introduction to z-scores and the empirical rule. And in the next week, we're going to go over simple linear regression in more detail. And then after that, we're going to go into sampling and then a lot more different tests that we have. So if anyone has any other questions, they're more than welcome to email me, and I'll be back on tomorrow for another section. But good luck on your problem set, your mission, in case we don't talk in between then. And feel free to use the discussion forum or reach out to the teaching staff, and we're happy to help answer it if you have any other questions. Okay, so thanks for attending, everyone, and good luck with all the material. Hope to speak to you soon.